That just sounded like a prayer starting.
No, she wasn't quiet. So we're going to dedicate this problem to Daisy.
It sounds like you're saying a mass.
With the special intention of Daisy. All right, so problem number 38. We have the function y is equal to x squared. When I post this video on the internet, I'll email her and then send it to her, and then I'll have to explain why we dedicated this problem to Daisy. So anyway, hold on, don't go down memory lane. Let's finish this problem. Verify that the function is continuous and state its domain. Indicate which theorems you are using. So there's a couple of theorems that we could use to indicate its domain. If you look in your textbook, theorem 7 is the main one, but there's also theorem 8, which is the intermediate theorem, and there's also theorem 6, which is the sum, difference, and all that. And so I'm gonna because I have a sum here, not your textbook. I could really go crazy, but theorem 6. So and these are for continuity, right? So we're proving continuity, right? So theorem 6 is that if I have f plus g, where f is continuous, f plus g is continuous, so long as f is continuous and g is also continuous. So if I separate, and the reason I went with that is, notice it's the sum of two functions, all right? So g is also continuous. Now, if that's the case, I could say that y is equal to f plus g. And so what does that mean? Well, we would say that f of x is equal to x squared. That's a continuous function. And then we could say that g of x is equal to the cube root of 4 minus x. Now, I would be happy with that there, but we could, if we really wanted to, go one step further, dive a little deeper. What could we do if we wanted to? Anybody have any suggestions? Well, for example, x squared is x times x. So I could say that f of x is the sum of h and k, where h equals k, and h equals x and k equals x, and so there's that product rule from theorem 6. I suppose I could use theorem 7 here and do the composite function, and so I'm going to do that. But I just want you guys, the answers will vary, right? But I could say that g is equal to, let's do, g is equal to h plus k, right? Or no, not g plus, or not h plus k, but we would say h of k, right? We would say h ok, right? That's the composite function. In other words, g of x is equal to h of k of x. And so then what would you define h as? We could say that h of x is equal to the cube root of x, right? Which is a continuous function. And then you could say k of x is equal to 4 minus x, which is also a continuous function. And then you could break this down. You could say that 4 is a continuous function, minus x is I mean, you could literally go crazy with this thing and break it down into one monomial for every you could prove that every monomial term is a continuous function, right? Okay, so your answers will vary a little bit, but the goal is to apply either theorem 6, which is this. Remember, theorem 6 said f plus g, f minus g, f times g, f divided by g, as long as g doesn't equal 0, as long as those functions are continuous. If the individual functions are continuous, then the sum, difference, product, or quotient are also continuous. And so this is enough. By letting f be f of x, oh, I already wrote it down over here. F of x would be x squared and stuff like that. And g would be cube root of 4 minus x. And then if you wanted to, you could dive even deeper. This would be, this right here would be theorem 7. Or is it theorem 8? I forget. That's theorem 7. The composition of functions. If the individual functions in a composite function are continuous, then the overall composite function will also be continuous. Does that make sense? Okay.